2j minus k. And then I'm taking the cross product with 4i minus j minus 2k. Something like that. Alright. And let's take the cross product of these two vectors here. So this would be technically my a1, my a2, my a3. This would be my b1, my b2, and my b3. Okay? Now, I could, I'm just going to rewrite it as this guy here. As 3, 2, negative 1, 4, negative 1, negative 2. All right? So the first term is going to be I times this determinant here. I times 2 minus 1 minus 1 minus 2. Okay? Next one will be minus j times 3 minus 1, 4 minus 2. And then it would be plus k, 3, 2, 4 minus 1. Right? And from here, it'll be easy to calculate. 2 times negative 2 is negative 4. Right? And then I'm taking this, I'm subtracting. Minus 1 times minus 1 is 1. 3 times negative 2 is negative 6, and I'm subtracting 4 times negative 1, which is negative 4. 3 times negative 1 is negative 3, and I'm subtracting 2 times 4, which is 8. All right? Now, this is just the final coefficient. Minus 4 minus 1, minus 5i, minus 6 plus 4, minus 2j, minus 3 minus 8, minus 11k. And this is the cross product. Alright? A bit easier, like, Kayla, what do you think? We didn't cover this form, I don't think I had time. Do you think this is a bit easier to look at it like this? Yeah, probably. Okay. Alright, so now that we kind of have that, let me give one example and have some brave soul come up and try it. Alright? I have I minus 2j plus 3k. And I want to cross product with minus 2i plus 4j minus 6k. Okay? And I want to try and come and solve this. Alright? There you go.
That's 6.
Yeah, so minus 6.
So I do like
So yeah, so you're kind of covering the row and column with I.
that would be minus.
Almost. So you're taking 4 and you're subtracting negative 2 times negative 2.
I always do
You're good, you're good.
that. Okay.
Alright, so what's your answer?
So I is 0 minus
It's all 0.
Yeah.
Awesome. I did it on purpose. Now, for the extra vigilant of you, you might have noticed that if I factor a negative 2 out of this, I just get I minus 2j plus 3k. which is exactly what this vector is. So I'm essentially taking a vector and I'm taking the cross product with another vector. Awesome, that's exactly what we're supposed to get because they're parallel. Alright? That makes sense actually. Like anything else that's a bit confusing about the cross product before I move on?
Again, with the negative j, it doesn't seem like it affected the cross product of that one.
Well, I mean, if I had a plus here, oh, for this one?
Yeah.
If I had a plus here, it would be plus 2. Right?
Yeah, but it would still come out as negative 2.
No, it wouldn't.
Negative 6 plus 1.
So, okay, so the thing is, 3 minus 1, 4 minus 2. Let me put a negative in front of here. So I get negative 6 minus negative 4, okay? Which is negative 6 plus 4, which is negative 2. Yeah. Oh, wait a second. Did I make that? Did I do an oopsie? Yeah, I did do it. It's meant to be a plus initially. Right. So I have plus 2 here, right? If I made this a plus, I would just end up not having a minus here. So I would get minus 2 in the end. Now there is a way to have a plus in front of it and still do the determinant. You just switch these two columns. So you make this minus 1, minus 2, and then 3 and 4. So it's minus 4 minus negative 6, which is plus 2, and then multiply by positive. So I end up getting 2 in the end. Get what I mean? Just a little food for thought. The cross product is a really annoying tool to start working with, but very necessary. All right, now let's actually get on to some more fun stuff. All right. The next part is components of vectors. Just so we understand that there's kind of another alternative way to represent. So let's say I have my x-axis and my y-axis, and I have some vector A here. And there's some angle here too. This side and this side. This side would be the magnitude of A times cosine theta, and this side would be the magnitude of A times sine theta. The reason we do this is if you take a look at your unit circle, I have this guy here, like the radius being 1, and I have some angle theta here. We define sine theta to be this guy. And we define cosine theta to be this guy, right? Ever remember that? Okay. And you know, it's a right triangle. So this squared plus this squared is going to be 1, right? Because the side length is going to be 1, or the radius is 1. Sine squared theta plus cosine squared theta is 1. Pythagorean's identity. Now, if I do this here, I get a squared cosine squared theta plus a squared sine squared theta is the magnitude, the length of this side squared. So a squared. This is consistent with Pythagorean's identity. All right? Sometimes you will denote this ax or ay, and you'll denote this ax. And just know that they're kind of interchangeable notations. A sub y and a sub x, essentially. It's a subscript. All right? So we have that. Little food for thought. This is going to pop up quite dramatically later on. Now, let's actually get into some of the calculus. Y'all are familiar with calculus? I hope so. Let's. I'm going to assume you know how to take derivatives and integrals. I will not take any time to explain any of the basic differentiation and integration, because this is kind of I hope you're in this class because you took calculus 1. All right, so we're good. All right. I'm going to denote a vector in 3D space to a point we'll call x, y, z, okay? And I'm going to call this vector r. Essentially, if I'm going from the origin and pointing to some point, right? some position in space. I have a special name for this vector. I'm going to call it the position vector. Okay? The position vector marks location in space. All right. That being said, I can rewrite R as xi plus yj plus zk, right? Awesome. Now, let's say now, instead, that x, y, and z are functions of time. So this becomes x of t I plus y of t j plus z of t k. All right? This essentially means that as time goes on, this point will change. So maybe after some time, it's over here, and then maybe over here, and then maybe over here. Maybe it goes over here, and over here, and it just continues to move. And over time, I can trace out the path of these points. This path that I've traced out is what's known as a trajectory. All right? The trajectory of is essentially just a path in space. That's really it. If I talk about an object, I want to. One of the more pressing questions in physics is to find out where it's going, where it is, where it's going, what's it doing. All right. Now it could move to particular points faster than others. So, for instance, I want to find the rate of change of position with respect to time. Let's say it's going from here to here, and it moves for some increment, delta t. You can make those kind of incrementation arguments all you want. What you'll end up with is the derivative. I can actually differentiate this vector, and I define it as some new vector v. This v is the velocity vector. This velocity vector is going to be dx dt I hat plus dy dt j hat plus dz dt k hat. I'm differentiating this entire thing. But Hunter, you might say, this is a product between xt and I, right? X of t being the function and I being something that's multiplying. So when I differentiate it, shouldn't I use the product rule? No, don't do that. Because, I mean you can, but you'll find out that it doesn't really matter. I is constant, j is constant, k is constant. There's no amount of time that you can wait until I moves off of this axis, right? Essentially, what you're only taking derivatives of x, y, and z, and you're kind of finding where it's going. This is what's known as like a tangent vector. If it's tangent to a path, it tells you kind of where it's headed as opposed to where it actually is. So the position vector would be something like this, whereas a tangent vector points in a different direction, right? It's a very helpful thing, actually. Even further, I can go a step beyond, and say, hey, how about how the velocity vectors change? How do they change over time? And so what I'm left with there is the next derivative that we want to talk about, dv dt. I'm going to denote it as a, which is essentially d squared x dt squared I plus d squared y dt squared j plus d squared z dt squared k hat, right? We're essentially, so position is where is it? Velocity, how is that position changing over time? And acceleration, how is that velocity changing over time, right? Now, those are the three general quantities that we're concerning ourselves with for now: position, velocity, and acceleration. We can go even further and say, okay, how is acceleration changing over time? How is the derivative of acceleration changing over time? We can, but we're not going to yet. I do want to cover something like that if we have time today, but for now, it's not really important. One other thing though, what is the dimension of my position vector? What would that be? What kind of units would I be using to describe this?
What are we assigned to it?
Yeah, I mean, yeah. But am I going to use seconds to tell you how like where you're at? Right. I'm going to use like meters or feet or something like that. The dimension of this position vector is dimension of length. The dimension of the velocity vector is going to be dimensions of length per unit time. The dimension of the acceleration vector would be dimensions of length per unit time squared. And we can keep going on and on and on and on. What is this? Why did the units change? All I did was differentiate them. Well, the derivative actually has units. It's weird, but it does. Essentially, what I did here, the kind of units for derivatives would be 1 over whatever they're differentiating with respect to. So I'm differentiating these quantities with respect to time, so its dimension would be 1 over units of time. If I differentiate with respect to distance, it would be 1 over units of length. I can actually go backwards with this too. I can say the integral of v with respect to time would be r. The integral of a with respect to time would be v. The integral then is going from here to here to here. So the integral with respect to time would have units of t, essentially, units of time. All right? Just food for thought, really. You're not going to actively use this, but it's really good to understand where these changes in units come from, especially when you're doing dimensional analysis. That being said, now we can actually start doing the first physics problem in this course. We haven't done any physics yet, guys, I know, I'm sorry. But rest assured, we can actually start doing that now. This is what my lecture is really focusing on today is kinematics. Essentially, how do objects move? What time is it? Okay. Oh, geez, we're good. We're only an hour in. Dang, nice. All right. Kinematics is essentially the study of kind of like how things move, not concerning mass. Essentially, working with these 3 quantities, R, V, and A. These 3 quantities are the most important aspects of kinematics. So let's just say I'm moving along the x-axis, okay? And I have some constant acceleration. Either a car is speeding up, or like a plane is slowing down after it's landed, or, you know, something like that. Or gravity somehow switched and it's in that direction now, and I'm falling this way. Which is weird, but, you know, it could happen. So essentially, what I mean is my function, my acceleration function, is really just a function, a constant in the x direction. That's it. I could have one in the y direction, I could have a component in the y direction, I could have a component in the z direction. It gets a bit more complicated that way, but let's just assume there's an acceleration in the x direction for now, right? How do I get velocity and position from that? Well, how did I do it there? How do I get velocity from acceleration? I integrate. Okay? So the integral of acceleration would be velocity. If this is constant, it's really just going to be at plus some constant c. Well, and this is velocity as a function of time, right? So then, what would that constant be at the end there? Let's see. Well, if I want to just observe the constant, I want to get rid of this. And making that 0 would be a nice way to get rid of it. V of 0, which is just a times 0 plus c, would just be c. The velocity at time t equals 0, essentially when I start my stopwatch, or when I just like start actually timing something, or maybe I started time at -1, but conventionally speaking, it's just the initial time. If I start my time at t equals 0, this is going to be my initial velocity. I'm going to call it v naught, or v0, or whatever you want to say. Okay? So the first of my kinematic equations is obtained. Actually, let me erase all this. Okay. So I'll just keep track of my kinematic equations. Oh, and these are the kinematic equations for constant acceleration.
I have to go, thank you though.
Oh yeah, no problem. This will be posted on the groupie most likely.
Okay, perfect.
So you won't be missing out for too long. Okay? So we have the kinematic equations for constant acceleration, and that's what I'm getting here. The first of which would just be my velocity function. V naught plus AT. All right, now from there, how do I get position from velocity? Integrate again. So my position from my velocity is just going to be the integral of my velocity function. So it'll be V naught t plus 1/2 AT squared plus some new constant. Okay? This new constant is just going to be, this new constant is going to be essentially, like with V naught, what happens when my position is at 0 time. If I set t equal to 0, this is my initial position. So my x naught, or my x function, is x naught plus V naught t plus 1/2 AT squared. All right? That's actually really nice. Let's do a few more of these particularly. Now, for instance, let's say that I didn't have time as a parameter, and I just wanted to kind of work on, if I didn't want to discover time at all, and I just had position and velocity, how would I do that? Well, I can solve for t in my first equation. So t would be v minus v naught over a, right? And my x would now be x naught plus v naught times v minus v naught over a plus 1/2 a v minus v naught over a squared, right? We can simplify this further. I'm going to subtract x naught on both sides, and so I end up getting v naught v minus v naught squared over a plus 1/2 a times v squared minus 2 v naught v plus v naught squared all over a squared. Ugh, oh, it's just getting uglier. I'm going to end up having, this a is going to cancel out with this a, so I'm going to end up having 1a on the bottom. So I'm just going to multiply out by a on both sides, and by 2, so I can get rid of that 1/2. So 2a times x minus x naught is going to be v naught v minus v naught squared plus v squared minus 2 v naught, oh sorry, multiply these by 2. 2 v naught v plus v naught squared, right? These are going to cancel, and these are going to combine to just be minus v naught squared. Okay? I'm going to call this, which is essentially my final position minus my initial position, I'm going to call it D for displacement. So I end up with 2AD is equal to V squared minus V naught squared. Also, just as an aside, who here does not know the difference between distance and displacement?
Isn't one positive and one's always, it could be positive or negative?
So essentially, what I have here, let's say I'm just going to take a walk around the classroom, and from there, you take a tape measure, and you just measure the distance that I have walked, right? The distance is exactly the length of the path that I am taking, right? But at the end of my walk, if I end up back where I started, I have not really changed positions at all. Displacement is the net change in position. Distance is the length of the path. So displacement would be final minus initial. All right? All right. So I end up with, in essence, an equation that looks like this. V squared equals V naught squared plus 2AD, where D is just final minus initial. Awesome. That being said, that's our third of the kinematic equations. We can do one more, pretty much. And it's not really that important, but I think it's nice for the culture. I have this function v equals v naught plus at. If I start out at an initial velocity, this is going to be a linear function, right? And I stop it at some arbitrary point for v. And I want to find the average value here. The average velocity is going to be the final plus the initial, just divided by 2. Easy peasy. That's the last one, really. Of the kinematic equations. We have now set ourselves up to talk about like the first real world example.
Isn't that one times t?
What?
That last one isn't times t?
Oh, no. This is just units of velocity.
Um,
Right, make sure your units match up, right? Essentially, take a look at this. If I have velocity on this side, every term here has to have units of velocity, right? If this is units of acceleration, then acceleration times time would have to give me units of velocity. Acceleration has units of L over t squared, and time just has dimensions of t. And I'm going to end up with L over t, which are my dimensions for v. You might want to get into the habit of doing this particular thing just to make sure your dimensions match up. It's very nice to have this at your disposal because it double checks you in the instance of being, making a mistake. That being said now, let's make a few modifications to these equations. Let's actually, instead of acceleration being in the x direction, let's have gravity in the actual direction it is. I'm going to say this direction, down, up, it's y. And I'm going to instead then, my acceleration vector my acceleration vector is not going to be a I hat. It is going to be minus g j hat. All right? It's going down in the negative y direction, and it's got a magnitude of g. Well, you're aware of what g is. G is 9.81 meters per second squared. You're familiar with that. What we can do then is say, it's a decent, it's the quantity that we use all the time. Some people say, oh, it's 9.8. Some people say, oh, it's 10. It doesn't matter what number you use as long as it agrees with the sig figs of the problem, right? So if you have 3 sig figs, use 9.81. If you have more, use more. They probably have G figured out to a ludicrous precision. So instead of that, I'm just going to modify my equations now. With gravity, this equation, and I'm talking about y velocity, is v naught y minus gt, right? So if it's y velocity, this equation is no longer along the x-axis. It's along the y-axis. Y equals y naught plus v naught y t minus 1/2 gt squared. This becomes vy squared equals v naught y squared minus 2g y minus y naught instead of d. And our average velocity is just going to be, the average velocity in the y direction is just going to be vy plus v naught y over 2. There is one more thing that I want to take into account now, and that's x motion. If, let's say that Rachel insulted my mom or something, and I got really mad, and I wanted to throw a table at her, and I pick up this table with my monstrous strength, and I throw it at her. And gravity will only affect the table in the y direction. It will move at a constant velocity this way. There is no acceleration in the x component. You can think of it like this too. You can think of it as 0 times I minus g times j, right? And that would actually probably help you figure, like see it a little bit more. So the x acceleration here is going to be 0. Making this equation simply x naught plus v naught t, or x equals x naught plus v naught xt, right? That makes sense. Okay, so we're good on that. These are commonly the 5 kinematic equations for, projectile motion. And that's what we're going to call this type of motion. If I throw a table at Rachel, that table is a projectile. All right? So we can now move on to a real physical example then. Like, if I throw it at Rachel, I'm going to erase this. Is everyone all right with this? Okay. So, let's only talk about the one-dimensional case for now. Let's say my aim is bad and I just throw it up. All right? So, this is me, and I've thrown an entire table up in the air. All right? It's going to follow a path like this, essentially. So, and this is the y-axis. If I follow y as a function of time, essentially mapping out every point, assuming, let's say I just start from ground level, and where my initial height is 0. It's going to be a parabolic path, okay? That parabolic path now has a few quantities of interest that I want to calculate. So for instance, I want to calculate the time